Now I'm going to present the final element in our discussion of measurement issues in economic history. What I want to discuss with you now is how we measure technological progress. To me, this is maybe the most interesting of these three topics. Of course, quantifying growth and change and assessing changes in living standard is really important. It's essential. But what's also nice and maybe more interesting to me is being able to quantify exactly what has grown and changed, and maybe even deeper, like why there was growth in the first place. This idea, how we measure technological change, is going to give us some of these clues. So we're going to reduce the world quite a lot and assume that we're working with an economy that has an output Y and three main important inputs: land, labor, and capital. Land we're going to call T, labor is L, capital is K. I think labor and capital, that's sort of from the German tradition, I think, like K, Kapital from Marx. T, I think, comes from the French. I won't say it, but some of you guys are going to know what T stands for in French. And you see this everywhere, okay? This is not my nomenclature. This is how you usually see these represented in the economics and economic history literature. And we're going to express the relationship between that output Y and inputs T, L, and K as a production function, where output Y is a function of L, K, and T. A really common form of this production function, which I think you've all probably seen before in intro, micro, or macro, I hope, is what's called a Cobb-Douglas production function. We'll work with this in our class, and just as an aside, by the way, a reason that economists like Cobb-Douglas production functions is because they tend to work really well empirically, meaning like with real data. So this is what we're going to stick to now, even though they're very simple. So in a Cobb-Douglas production function, output Y is expressed as labor to the power A, capital K to the power B, and land T to the power C. And a really kind of nice trick here is if I take natural logs of this whole function, I get the log of output Y equal to, when you take a log, right, you bring the power down, so that it's A log L plus B log K plus C log T. That's really nice. And, for those of you who've taken stats or regression, there's something kind of really nice about an equation like this, which is that it sort of kind of looks like a regression equation. And indeed, one can take something like this to the data just that simply. But if you take a look at here, right, we've got some elements, like we know about output and the inputs, but what are these A, B, and C? We're going to call these weights. And we'll impose a pretty common assumption, which is constant returns to scale, in which case these weights all add up to 1. By the way, if you're interested, I can show you how to do this, but we're going to work with an even more versatile form of this production function, which is one expressed as percentage changes. If you differentiate this production function with respect to time, what you can actually arrive at is a slightly different form of it, which is really useful. And what we're going to have here instead is an expression where the percentage change in output is equal to A times the percentage change in labor plus B times the percentage change in capital plus C times the percentage change in land. That turned out to work really nicely empirically, and it's going to help us try to understand what percentage changes are due to what other percentage changes, help us relate changes to changes. To see how something like this would work, we're going to work through a numerical example. So let's proceed by trying to relate what we have in the previous slides to this data. So just to spell out the table for you, what I've got here is 2 years worth of data from some arbitrary years, 1750, 1760, from a fictional place. And I've got here output, labor, capital, and land. And what I've done below is already evaluate for you the percentage changes. So if I go from 100 to 110, that's a 10% percentage change, right? Because later minus earlier equals 10, divided by earlier, 100, equals 10%. So you can see these are not decimals, these are percentage changes evaluated in whole numbers, so there'd be a 10% there. Now, another detail here. let's try to figure out what the weights are for this example. They are actually implicit in the data that I've given you. So this may be like reaching way deep into your mind if you ever learned it, but there is a way we can figure out the labor share, the capital share, and the land share, and hence the weights from this data. And here's how. As it turns out, the labor share of output will be equal to the weight A times output Y. So let's make an assumption here. So assume that I know that the total value of output is $100, that wages are $30, capital income is $50, and rent and land is $20. What then are the weights that we would use, A, B, and C? Well, let's take a look here. So if I want the labor share, $30, to be equal to A times the value of output, which is 100, that would necessitate that my labor share A is 0.3, and then so on, right? Our capital share is 0.5, or I'm sorry, our capital coefficient, our weight is 0.5, and then the land coefficient, C, is 0.2. So then let's try to calculate the percentage change of output given those weights that we have and the percentage changes we have in the inputs. Okay, so the coefficient that we have on labor is 0.3. Let's multiply that times the percentage change in labor, 2.5, and so on for capital and land. And now the number I arrive at is 7.75%. But I thought we already knew that percentage change in output was 10%. It looks like math doesn't work. It looks like I've done this wrong. Well, we need something that gives us a little wiggle room with these numbers. We need a fudge factor because indeed, sometimes in an economy or any closed system, you get out more than it looks like you should get given the change in the inputs. We're going to call this fudge factor the residual R. We are literally going to add it on to the end after our weighted percentage changes in inputs. Now, once again, if you've taken stats or regression, this now starts to look very much like a regression equation. We're even calling this last term a residual. In our example that we've just calculated, our residual then would be what we should have gotten minus what we got. So 10 minus 7.75 or 2.25%. That's going to make these two sides of this equation agree. So that's math, but that's not economics. For this to be economics, we need some interpretation for this residual R. What is this thing? Okay, well, one thing it can be is just measurement error. In other words, there's a mistake in the data or there's some noise in the data. And this could be introduced from several places. There could be some noise in the weights, in our measures of output, collected from some old manuscript somewhere or something, or in our measures of the inputs. But there's another way to get out more than you put in, essentially, to get out more than you would have thought. And this could be technological progress. Okay, our production function, our production system, our way of producing Y from these inputs has somehow become more efficient, so we get more. This is the very nature of what we mean by technological progress. Finally, there's another way to get out more than you put in, and that's through some change in the rules of the game or institutions. We'll call this institutional change, and we will study this in great detail in a couple of weeks. So these are really three separate possible R's. How do you know which one it is? You can't. R is a measure of our ignorance. I don't know how much of the R that we might get would be due to 1 versus 2 versus 3. Unfortunately, we cannot know for sure. And I'm going to drill this into your heads a little bit in the problem set that you're going to have to do in a week.